Hey everyone, and welcome to this explainer. Today, we are taking a massive leap forward in our C programming skills. We're moving away from the single flat line of a standard loop and stepping into the incredibly powerful multi-dimensional logic of nested loops. Think about the pixels on your screen forming an image, or a digital chessboard, or even the vast amounts of data organized in a spreadsheet. They all completely rely on this foundational concept. If you've ever wondered how programs generate massive grids, 2D arrays, or really complex visual patterns, well, you are in exactly the right place. So let's dive right into this.
To start, think of a Russian nesting doll. A nested loop simply means we have an inner loop living entirely inside an outer loop. Instead of just executing a single block of code and moving on, the program suddenly encounters a whole new loop that it has to fully process. It's literally a loop within a loop. And the best part, this multiplies the power of your code without multiplying the lines you actually have to write.
Here's a quick look at our agenda for today. 1. The nested loop concept. 2. Tracing the loop indices. 3. Building a custom grid. 4. Changing patterns and pyramids. And finally, 5. 2 practice challenges to test your skills.
Let's kick things off with Section 1, the nested loop concept.
We're going to start with an analogy to really ground this abstract code into something tangible. Think of an old-school typewriter. This is actually the perfect analogy for nested loops when you're printing grids. Your outer loop acts as the carriage return. It's your line counter. It dictates exactly which row you are currently on. Now, for the younger programmers out there who might not have ever used a typewriter, just think of the carriage return as the literal new line character in C. The inner loop, on the other hand, represents the individual keystrokes. It runs across the page, printing the characters one by one to form the columns. So the inner loop does all the fast, repetitive typing horizontally, while the outer loop slowly moves the paper down to the next line vertically.
Moving right along to Section 2, Tracing the Loop Indices.
Okay, we really need to look at the internal clockwork of the code now. Pay close attention here, because understanding this execution flow is honestly the biggest hurdle most programmers face. Let's walk through the step-by-step lifecycle of the compiler. Step 1, the program enters the outer loop. Step 2, it immediately hits the inner loop and enters that. Now Step 3 is the secret sauce. The inner loop must complete absolutely all of its iterations. Whether it's counting to 2 or counting to 100, it has to finish entirely. Only then, at Step 4, does the program finally break out of the inner loop, increment the outer loop, and start the whole process all over again.
The absolute best way to track this in your own code is by adding a simple printf statement inside the inner loop to directly print the integer values of your variables. If you do that, you'll generate a table just like the one we're mapping out. Let's say we have an outer loop using variable I and an inner loop using j. For the very first execution, I is 1 and j is 1. On the very next iteration, I remains 1 while j increments to 2. See that? The inner loop cycles completely while the outer loop's variable remains totally static. Once j finishes its cycle, I finally updates to 2 and j resets completely back to 1. Using that printf debugging trick is incredibly valuable when your loops aren't behaving quite right.
And this brings us to a golden rule pulled directly from our source material. To complete one iteration of the outer loop, you have to first escape the inner loop. The inner loop essentially acts like a trap. It holds the execution flow captive until its specific condition evaluates to false. Understanding this trap is the absolute key to mastering two-dimensional code.
All right, Section 3, Building a Custom Grid.
Theory is great, but let's actually put this into practice by building a custom grid where a user gets to define both the shape and the symbol. Let's compare the distinct jobs of our two loops. The outer loop parameters are bound by the number of user-defined rows. Its main job, right at the end of its cycle, is just to print a new line character pushing us down the screen. The inner loop is bound by the user-defined columns, and its only job is to repeatedly print the chosen symbol. It's a great division of labor. One handles vertical space, the other handles horizontal space.
But as our sources point out, there is a massive trap when asking a user to input these parameters to build their character pattern. You'll naturally use scanf to get the integers for rows and columns. But here's the catch. When the user hits enter, a new line character gets trapped inside the input buffer. If you immediately try to scanf a character for your symbol right after that, your program will pick up that invisible new line instead. This exact invisible new line has caused millions of headaches for C students over the years. So the absolute crucial point here is to clear your input buffer, often by doing a dummy read of a character, before you ask the user for their actual grid symbol.
Moving on to Section 4, Changing Patterns and Pyramids.
A basic square grid is just the starting point. By slightly altering the inner loop limit, we can unlock entirely new geometric patterns. Take a right triangle, for example. The logic here is beautifully simple. The outer loop I still counts the rows, but look at the inner loop j. Instead of running to a fixed column number, we tell it to run until it equals I. So, on row 1, it prints 1 star. On row 2, j runs twice, printing 2 stars. By binding the inner loop's maximum limit to the outer loop's current index, the shape grows dynamically line by line, perfectly building our pyramid. Now, there is a hidden multiplication rule behind these loops that you really need to be aware of. If you have an outer loop set to run 6 times, representing 6 lines, and an inner loop set to print 5 stars per line, your inner print statement actually executes exactly 30 times. The outer loop runs 6 times, sure, but the inner loop runs 30 times. Keeping this math in mind is absolutely vital for understanding how much work your program is actually doing behind the scenes, especially as your datasets get larger.
Finally, let's jump into Section 5, 2 practice challenges.
All right, let's test your understanding with 2 practice challenges, based on the exact logic we've just covered. Here is challenge 1. Imagine your outer loop runs exactly 3 times, but inside, your inner loop is a countdown. It initializes j at 5, runs as long as j is greater than or equal to 1, and decrements j each time. Inside that inner loop, you are printing the value of j. What is the final output going to look like? Take a second to mentally trace that execution flow.
Got it? Okay, here is the result. The inner loop successfully counts backward. It prints 5, 4, 3, 2, 1. And because the inner loop must finish entirely before escaping, it prints that full countdown on one single line. Then the outer loop triggers a new line, and the whole countdown repeats. It does this a total of 3 times.
Okay, ready for challenge 2? Let's talk about the break statement. The break keyword stops a loop right in its tracks. But in a nested environment, placement changes everything. What happens if you put a break statement inside the inner loop versus putting it inside the outer loop? How does the logic change?
The answer reveals a major logic difference. A break statement only escapes the immediate loop it resides within. So, an inner break will stop printing columns for that specific row, but the outer loop, it will just move on to the next line and try again. However, if you put the break in the outer loop, you escape the main sequence entirely, meaning the entire grid just stops printing instantly.
Well, you've officially mastered the 2D grid, but I want to leave you with this final provocative thought. If an outer loop I and an inner loop j create a 2-dimensional flat grid, what kind of structure do you create if you add a third loop, k, nested entirely inside of j? Are you suddenly programming in 3D space? Think about how that flowchart would look and what kind of complex, incredible data you could generate with that. Thanks so much for joining this explainer, and keep coding.
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos are coming soon.